Last lecture we discussed about the characteristics of dynamic systems. We said that the mass is important because inertia force is generated from the mass proportional acceleration. We need the restoring component for recentering purposes. We have to also represent the frictional component, and of course an external force is required to cause vibration or to set a motion in place. So, mass expressed in kg, stiffness expressed in Newton per meter, damping expressed in Newton per meter per second, and external force f of t is a time history or a spectrum. Now, the question comes, there are 4 ways by which you can mathematically model a single degree freedom system. One is a simple spring mass system. Other can be a torsional pendulum. The third one can be a mass spring pulley system. The fourth one can be a base isolation model. Wherein in all these cases there is only one independent displacement degree of freedom, which makes the system as single degree of freedom system. So, degree of freedom is a term related to individual number of individual displacements. It is not the point where the mass is concentrated. We already said we lump the mass at this point because we are measuring, or we are interested in measuring the inertia force. Therefore, it is always better to lump the mass at the point where your displacement is to be measured. Therefore, we say that more or less the point where the mass is lumped is almost same as that of degree of freedom, but the definition is not that. It is independent displacement coordinates required to express inertial component in a given system. Now, today we will talk about how to mathematically model this. The moment I say mathematical modeling, I must try to get out or find a mean to find the response of the system. As we all know, the given system is dynamic in nature, the response will also be a function of t, and we all know if we differentiate with respect to time, it becomes velocity. If we differentiate further respect to time, it becomes acceleration. So, these are the 3 set of responses I generally require or acquire from a given system if the system remains dynamic in nature, because the force excited is dynamic in nature. There are 4 ways I can always represent a given system single degree mathematically. There are 5 ways I can write equation of motion. Now, to solve the mathematical model or the analytical model using equations, I must express the whole behavior in terms of an equation which represents the displacement of the body with respect to time. We call this as equation of motion. Motion terms related to displacement, and I am going to write an equation. Obviously, we know the displacement is going to be function of time, therefore, it is going to be a differential variable in time. Therefore, the equation what you attempt to write will be a differential equation. Okay. Now, we already said it cannot be partial differential equation, because though mass may vary along its length, but we have lumped them at a specific point. We are discretizing the mass and we are not considering the variation of mass along the length. Therefore, no 2 variables are considered at a time, we will consider only one variable, that is a time domain variable. So, I will get simply ordinary differential equation. So, there are standard procedures available in mathematics to solve an ODE, which we will quickly see once we write the equation of motion. There are 5 ways by which I can write the equation of motion. Let us start from a simple mechanism. Let us say the first one is simple harmonic motion, which I already studied in physics. Of course, the methods of writing equation of motion is applicable to all the 4 models. You can write equation of motion to any one of them by all these 5 methods. We will take up one simple example of spring mass system and deliberate it. In subsequent examples, we will take up torsional pendulum, we will take up mass spring pulley system, we will try to demonstrate different methods of writing equation of motion to any one of them as and when we encounter the problem. Now, simple harmonic motion has got two characteristics. If you recollect back, the first characteristic a simple harmonic motion is having is that the acceleration is always proportional to displacement. The second, body will be always redirected towards the original position. Example, a simple pendulum. You take a pendulum suspended at an hinge, a bob, try to oscillate the bob will always have a tendency to come back to its neutral position after n number of oscillation, what we call them as period of oscillation. Okay. So, the tendency is to return back to its original or normal position. Okay. Technically and structurally, this particular characteristic is called recentering capability. This is one of the important characteristic a structure must have when it is subjected to vibrations. You must allow the system, or the system must absorb the forces and try to attempt to come back to recentering capability. Otherwise, the structure will impose or get encountered a permanent displacement which is undesirable. Today's structure is location GPS A, the structure does not have a recentering capability. Tomorrow the location of the structure will be GPS B, which I do not want. I want the structure to remain at A irrespective of the force acting on the structure. So, recentering capability is very important. This is exactly the same expressed in physics, saying that if the body is subjected to oscillation, the body will always have a tendency to come back to its normal position. That is, these two are basic algorithms in simple harmonic motion. I will use them here to generate equation of motion. Let us see how. Let us say mx double dot, that is the acceleration force, is always proportional to displacement. Now, to implement this second condition, I should say it is proportional to minus of x, minus because it is coming back. It is always directed in the opposite manner. If I try to pull the bob to the left, the bob will move to the right. If I try to push the bob to the right, the bob will move to the left. So, there is a tendency of the bob to always oppose the motion. So, minus. So, in simple terms, acceleration proportional to displacement, acceleration is equal to some constant. Let us say this constant is omega square of x. So, I should say x double dot plus omega square x is 0. Okay. So, this becomes my, whereas in this specific example omega square is taken as constant of proportionality. There is no other meaning for this, but it has got a specific meaning as I elaborated further. This is nothing but a proportionality constant, that is all, because this is proportional. I am putting a constant, equating it, and I am bringing it and rearranging the term, I get this equation of motion. Mx double dot, x double dot plus omega square x is 0 is the equation of motion as derived by applying the principles of simple harmonic motion to a vibrating body, which is nothing but a spring mass system, which is the first category what we have here. Now, we will apply Newton's law to write equation of motion. That is the second method by which I can write equation of motion, Newton's law. I will take up a simple system. Let us say it is having a spring. When you suspend the spring and leave it free, because the spring will have its self-weight, you will see the spring will elongate. Let us say that elongation is delta. Now, what is the force responsible for this elongation? Because elongation is always caused only by a force. You have a body, the body is displaced by its length, you need to apply a force to displace it by a length, or to contract the force your body, you have to apply a force in the opposite direction. There is a force required to cause displacement. Now we know that the spring has got a spring constant K. What does it mean? K is expressed in Newton per meter. It is, for example, for 1 meter displacement, let us say x Newton force is required to displace or to cause a displacement of 1 meter. So if I want to really find the force responsible to cause this deflection, then I can easily say that force is going to be K delta. Okay, K is the stiffness of the spring and delta is the displacement. So the force is K delta, because stiffness is force by displacement will give me the force which is causing this displacement. Okay. Now at this level, I suspend a weight W. Now this weight will again cause further extension, which now I call as x. That is the displacement. Now I draw a free body diagram. I pick up this, write down all the forces on that. So this is the body. The force acting now here is W, which is acting down. The force opposing this will be stiffness times of displacement and delta, is it not? So now there is a force balance. So let us apply that all downward forces positive. Write a force equilibrium equation. So plus W minus of K of delta plus x is set to 0. So plus W minus K delta minus Kx is 0, and that should be equal to mx double dot, that is my 4 Newton's law. So we know already this W which was caused by the force because the extension of spring will be cancelled. Okay. Now I say mx double dot plus Kx is equal to 0. So x double dot plus K by m, x is 0. If I say K by m is omega square, for K by m is expressed as omega square, x double dot plus omega square is 0 is as same as the equation of motion what we got from simple harmonic motion. Okay. The third method by which we can write equation of motion is energy method. Let us say kinetic energy can be expressed as half m v square. We already know it is half m x dot square because x dot is the velocity. Potential energy is half k x square for a spring system. Sum of energy in a given system has to remain constant. Law of conservation of energy. So I am going to try to do it in a different manner. I say differential of this plus differential of this is differential of this, which will be 0. So let us say differential of this. So d by dt of potential energy, which is d by dt of half k x square, which is half 2 k x x dot, d by dt of kinetic energy, which is d by dt of half m x dot square, which will be half twice m x dot x double dot. Let us rearrange here, half 2 kx x dot plus half 2 m x dot x double dot should be 0. So, simplify, x dot is common. So, kx plus mx double dot of x dot is 0. Obviously, x dot cannot be set to 0 because if x dot is set to 0, there is no vibration. Therefore, kx or mx double dot plus kx is set to 0, which implies that x double dot plus k by m of x is set to 0, x double dot plus omega square m set to 0, where omega square is k by m. Equation of motion is again same as you got from the previous two examples. So, in this case the energy method says that the sum of potential and kinetic energy should remain constant. I have taken expression for kinetic energy separately, P separately, differentiated them and equated here and arranged them, and I got the equation of motion, which is as same as Newton's law or simple harmonic motion. The fourth method is again an energy principle. Which is called Rayleigh's method. This method says the total energy in a given system is constant. We all know that potential energy is maximum at maximum displacement, kinetic energy is maximum at 0 displacement, whereas potential energy is 0 at 0 displacement and kinetic energy is 0 at maximum displacement. So, at any given point of time I can say maximum potential energy will be equal to maximum kinetic energy in a given system. Use this principle to write equation of motion. This is applicable only for single degree freedom system. For multi degree you cannot apply this. So, there is no serious difference in terms of writing equation of motion from Rayleigh's method compared to energy method. Energy method accounts for both the energy system present in that and saying the total energy is constant. Here it looks only for the maximum value of that and equate them. Okay. So, fundamentally by principle both of them address the same concept, but this is easy to apply to single degree and this remains as a concept. The fifth method by which we can write equation of motion is called D'Alembert's principle. It is a principle given by a scientist by name D'Alembert. We all know that Newton's law states that force is mass into acceleration. We all know this. When a spring mass system is made to move in a direction from left to right by a force, to stop the displacement of this body you can fictitiously apply mx double dot in the opposite direction to stop the motion of the body. On the other hand, if you have a body where the restoring force in the body is also offered by kx, that is the restoring force offered by the body. In addition to that, if you apply mx double dot in the direction opposite to motion of the body is moving this way, that is why restoring force opposite. If the body is moving from left to right, I must apply a fictitious imaginary force which is proportional to its acceleration in the direction opposite to motion. So, I must say this is mx double dot. Now, the body will be at rest, correct. Now, I combine them, mx double dot plus kx is 0, which means that mx double dot plus kx is 0, x double dot plus k by m of x is 0, or x double dot plus omega square m is 0 is as same as the one what we already have with us. So, D'Alembert's principle is only a concept, okay. It cannot be applied to complicated systems because it is very difficult to find out what would be the mass contribution on every mode of vibration to bring the body to rest. I can give an example. Imagine there is a stick model which has got only 1 degree of displacement, which is the tip. Let us say under any force, this hinged or fixed whatever may be, because the shape may be varying, I will make it as hinged. If it is fixed, the shape will vary. So, it will oscillate like an inverted pendulum. There is only 1 degree of displacement which is allowed to this mass. So, when the mass is pushed to the right, it will oscillate and so on and so forth. So, therefore, it is easy for you to apply a negative force which is proportional to its inertia in the direction opposite to the motion of the body. On the other hand, imagine a system like this, where there are 2 mass lumped, maybe this is hinge. On application of a force like this, the mass behaves like this. So, for example, this mass does not move, but this mass moves. On the other hand, this mass can move and so on. So, there are 2 displacements which are different. That is why they are called degrees of freedom. Degrees of freedom are independent displacement required to explain the position of a vibrating motion under the given force cycle or force system. Now, it is very difficult for you to apply a single inertia force which is proportional to which acceleration and which mass, okay. Or then in that case we must find out what is the mass contribution in total, then apply. Therefore, D'Alembert's principle, being a principle convenient, is applicable to single degree freedom systems. For higher degrees, this method is not followed, okay. Under the given 5 methods of writing equation of motion, we have seen that simple harmonic motion seems to be single and easy for a single degree. Similarly, D'Alembert's principle seems to be easy and simple for a single degree, and Rayleigh's method seems to be only a concept which is again a repetition of an energy method. So, we are left only with 2 methods where we can write equation of motion easily. One is the Newton's method, other one is the energy method. So, these 2 methods are generally practiced in dynamics to write down the equation of motion. Now, one can ask a question, we are interested in finding the response of the system. Why are we writing equation of motion? Where are we getting the response? Because our interest is to mathematically model the system, identify the degrees of displacements or degrees of freedom, and then write the equation of motion, that is what you are saying, but we are interested not in writing equation of motion, but to find the response of the system which is function of time. Interestingly, if you agree that this is my equation of motion for the given system, which is an ordinary differential equation in time domain, solution of this will be obviously x of t. Is it not? So, which I want. So, on the other hand, the steps involved in dynamic analysis are the following. There are two steps involved. One, for a given system, for an identified degrees of freedom, write down the equation of motion by some ways or the other. There are many ways to do this. One, understand and write the equation of motion yourself with any one of these two methods. The second is let others understand, you copy from them and write the equation of motion. So, first step is to write the equation of motion by hook or crook. Second is to solve the equation of motion to get the response. This is where we have mathematical interface playing. So, this is physics, this is mathematics. Okay. Now, if it is very simple ordinary differential equation, we have a handful method of solution where I can write the complementary function, the particular integral, then apply the initial and boundary conditions, solve them and get x of t in a full domain. If this one, each one of them becomes a matrix, maybe 6 by 6, 3 by 3, 2 by 2, they become a matrix. When they will become a matrix? When they become a vector. When they will become a vector? When there is more than one degree of freedom. On the other hand, when the system becomes multi-degree of freedom, then solving this or finding solution of this through standard solution is not possible. Okay. So, what we have to understand first is, let us write equations of motion for different systems, solve them, understand them for single degree first. As we move to higher degrees of freedom, we have to neglect or ignore the method by which I am writing x of t here, that is a standard ODE solution procedure. Then I have got to follow some numerical procedures which is available in the literature, because this is anyway mathematical. One of such method is the standard ODE solution. There are many other methods to find solution for a differential equation. We all know that. If you do not know that, we should know that. Okay. So, this is not the only way you can write the equation of motion solution. That is one of the ways. There are many other ways which we will see in the class. So, to start with, we will pick up single degree of freedom system, then we will try to write down the equation of motion, solve it using standard procedure and understand how qualitatively and quantitatively the result looks like. Okay. Now, let us get back to what are the essential characteristics of single degree freedom system model. Same question asked back again, which started this class actually. The essential characteristics are mass, stiffness, damping and force. These are the essential characteristics. Okay. Now, let us see, mass has to be present in any given system, otherwise there is no dynamic analysis, because we already said dynamic analysis is possible only when it has got a representative inertia force present and mass proportional. So, mass need to be present in a given system. If the mass is vibrating or if the mass is displaced, obviously the mass has to be brought back to its original position. That is what we call as recentering capability. That is one of the structural design requirement of any given system. Okay. You left your house to come to IIT for graduation, your father is expecting back to recenter, you will go back to your house. If you keep on moving ahead, then the problem is there, right. So, recentering is always required in every part of life. You come from the hostel, you are expected to go back to the hostel and expected back to come again to the classroom. So, there is always a cycle. So, a similar structural system has to have a recentering capability, because I do not want my system to keep on moving as I keep on exploring, okay, which is very ideal. Okay, I have a very interesting system where it keeps on moving, I keep on producing oil, I travel around the world like XYZ scientists and keep on accumulating barrels of oil and come and sell it in India, sometimes in Indonesia, sometimes China, which is very fantastic idea, does not work like that. My system has to stay, I have to do exploration, my platform has to recenter, of course with or without a permanent deformation. I cannot allow my platform to move as a while as it keeps on going, though it may be floating, very clear. Okay. So, recentering is essential. For that I need restoring force. If the restoring force is not there, recentering thought cannot be invoked in the design. Remember, these conditions of equation of motion in structural engineering applied to dynamics are all from physics, from the action of the structure. They have nothing to do with the dynamics as a subject. I am now posing requirements which are all required to be present in a given system. Then I will come back whether to do dynamic analysis or not. Now, damping is one part where I can mathematically represent the frictional force. I can even ignore it. Let us say my body is completely kept on a smooth surface, it does not develop heat, there is no friction, there is no loss of energy, there is no dissipation of energy at all. So, I can say the damping component, which is dissipating part of the energy, is not represented significantly compared to inertia force, compared to the restoring force relatively. Okay. Now, f of t may not be there. You may be wondering, sir, if f of t is not there, how the system will move? Okay. If I have no f of t and no c, I call this as undamped free vibration. The word free vibration stands for the system vibrating without any force. Now, again you have a serious question, if the system has no force, how does it vibrate? Okay. You set an initial vibration and leave the system free. You cause an initial vibration, let us say call the body to the right, then leave the body free. Oscillate the pendulum, let the pendulum tilt. Once you move the pendulum to the right and leave it, the pendulum will keep on tilting on its own. So, you have to set the motion on, but you do not require a constant force to keep the motion on. Okay. Therefore, I can say this is not present continuously. Initially this is certainly present. If that situation comes, it is called free vibration. If damping is not present, it is called undamped system. Okay. Now, the second case, I have anyway mass, I have anyway restoring force, I have damping also, I may not have the force. I call this as damped free vibration. Free because f of t is 0, damped because c is present. In this case c is not present, it is undamped. Let us see the third case, m is present, k is present, c is not present, but f of t is present. It is called undamped forced vibration. Undamped because c is not present, forced because force is present. Then do not get confused, so here also force was present. Force is continuously present, there is a time history of force, it is present all the time, like a wave, like a wind, etc. The time history of force which is permanently and continuously present in the system. But in this case, force was only allowed to initiate the motion, okay, then force was removed, right. The fourth could be mass present, stiffness present, damping present, f of t present. This is damped forced vibration. Now, I have a fifth system where mass is not present, stiffness present, damping not present, f of t present. Okay. This system is unacceptable, there is no mass. Okay. I have another system where mass is present, restoring force not present, for f of t present, unacceptable because I have a recentering capability. Remember, I am assigning these characteristics of dynamics in a physical sense to a given model, not in mathematical sense. So, never understand dynamics in terms of these clusters, understand dynamics in terms of physical meaning. If you understand the physical meaning, they will be associated to them automatically in your mind. Okay. So, do not try to understand the system by these cluster of words, though they are important, but understand them with the physical meaning of the characteristics of single degree freedom system, which is essentially required to classify a system as a dynamic system, which I already said in the last class. Okay. So, let us take up for start with, can I start from any vertical column, sir? Of course, this we are not anyway doing because it is an unacceptable system. Can we start anywhere? The degree of complication of understanding dynamics starts in the same hierarchy, easiest, easier, slightly tough, toughest. So, it goes the hierarchy in the same manner. So, for making it very easy, we must start with the system. So, we look for undamped free vibration model. What we are interested in? To find x of t. Why? We are interested in dynamic response analysis. We already know, using these 4 characteristics, if I form an equation of motion which is an ordinary differential equation and solve it mathematically, I will automatically get the solution. Okay, just now we saw that. So, we will pick up an example, write equation of motion, apply mathematical concepts to that, solve it as an ordinary differential equation, get x of t and try to understand qualitatively what do you mean by response analysis of undamped free vibration model. Is it clear? So, remember these tags are all associated in a physical sense to the characteristics of a system which is classified as dynamic system. Okay. They are not associated to, for example, you should never say free vibration means force is 0, no. Free vibration means one of the characteristic present in the system is not invoked, they are physical parameters, all of them are equally important, there is no one hierarchy over the other, but unfortunately this and these are the parents and remaining are children, but sometimes not only children take over the parents because of the intelligence, because of their arrogancy, because of the way they have been brought up, because the food what they eat, because the education what they receive, they take away the parents, but ultimately they remain children only. Okay. So, we will take up undamped free vibration. We already know that m is present, the equation of motion should be mx double dot plus kx plus 0 is equal to 0. So, I am looking for undamped free vibration response, that is what I want, that is what I want. So, I can even write in bracket mathematically C set to 0, f of t set to 0. Can I write this? Because this implies mathematically that this statement is correct. So, I pick up this mx double dot plus kx is 0. We already know how we wrote this equation, there are 5 methods, we already explained it. So, x double dot plus omega square x is 0, where omega square is k by m. I can write something called auxiliary equation, which is abbreviated as AE in mathematics, ordinary differential equation. It is written as d square plus omega square is 0, where d stands for d by dt of the variable, d square is d square by dt square of the variable, second derivative of the variable. Variable here is the x, which is the displacement, which is nothing but degree of freedom, x1, x2, x3, etc. So, the complementary function should be, let us say the root is minus omega square, which is I square omega square. So, d will be plus or minus I omega. So, this can be compared to alpha plus or minus I beta, where alpha is called the real part of the function and this is called imaginary part of the function. When I have both real and imaginary part, I can write something called the complementary function for a given ODE as a solution, which is given by this equation. So, I write the complementary function for this, which will be e power alpha x c1 cos beta x plus c2 sin beta. So, I should say x of t is e power alpha t, because that is the variable c1 cos beta t plus c2 sin beta, because I am writing this in the time domain. Okay, this is not t here, this is x simply, the solution. And we know alpha is 0 in our case, there is no real component. So, x of t simply becomes C1 cos beta t plus C2 sin beta t. Beta in this case nothing but omega. So, x of t is C1 cos omega t plus C2 sin omega t. Let us call this as equation 1. Now, there are two constants here, C1 and C2, which depends on the initial conditions of the problem. What are the initial conditions of this problem? When at t is equal to 0, there was no displacement. At t is equal to 0, the velocity is also 0. Let us apply this. So, the conditions are x of t is C1 cos omega t sin omega t, x dot of minus C1 omega sin omega t plus omega C2 cos omega t. Let us say at t is equal to 0, x 0, this term goes away, C1 okay. At t is equal to 0, x dot of 0 is omega C2, correct. So, I have now both the constants. Let me substitute in equation 1 and get the full solution. So, x of t, now I should say substituting the above in equation 1 I get, or let us say we get. That is a very interesting term here available in engineering generally. We always say we assume, let us assume. You will always see the teacher or the book author or the student does not say let me assume. Have you ever seen a book like this? See, it is a very interesting statement. It is very sarcastic to say also. We always say we because we unite all of you in the same boat. If you consider that the solution is answer is wrong and you say this idiotic solution, you are also an idiot. Okay. Therefore, there is nothing like I. We, let us assume. So, we are all joining hands in making a mistake, if at all so. So, you are with me all the time. You may not be with me physically. So, x of t is nothing but C1, that is x naught cos omega t plus x dot omega by omega sin omega. Okay. Equation number 2. So, I have the full solution now. Now, still one may not be happy to know, sir, where is the solution here? I am not able to visualize it physically. Yes, it is possible because I have not substituted t is 0, x is 0. I said x is nothing but x naught. That is, you can always start the problem with an initial displacement. Okay, you can always start the problem with the initial displacement, which you know. So, these are known values. These are known physical parameters applied to the system. This is physical parameter of the system, because omega is square root of k by m, because omega square is k by m. Okay. Now, omega is called, there are two meaning of omega. Omega is called circular frequency expressed in radians per second, where m is in kg and k is in Newton per meter. It is also expressed as f. F is called cyclic frequency and omega and f are related. Omega is 2 pi f. F is 1 over t, therefore, omega is 2 pi by t. Okay? So, they can be related. Now, we have learned two interesting parameters and result of this. What are they? One is the response of the system, which is the time history of the response, because it is time history, it is varying with time. Obviously, it should look like a history which varies with time. Okay? But this will be unfortunately superposition of a regular cosine and a sine wave. Sine wave and cosine wave has specific characteristic, we all know that. This is a typical sine wave, this is a typical cosine wave. Okay? So, superimpose them and run for n number of seconds, you get a combination of the final result, which depends on what is the weightage of the cosine function, what is the weightage of the sine function in the final result. You understand the point? Depending upon the multiplier of x naught and x dot naught by omega, the weightage of the sine and cosine function in the final solution will amalgamate to get a result like this. But this will definitely have a variation along its time domain. So, we call this as time history response, because it is varying with time. So, by writing equation of motion in simple harmonic or in any other method, we got equation of motion, which is fortunately for us an ordinary differential equation of second order, because the variable is of the highest order is 2, in this case d square y by dt square. So, second order. I have used complementary function and particular integral, in this case p a is 0, because the right hand side function of this equation of motion is 0. So, there is no particular integral for the solution, I have only one answer, which is complementary function, which is x of t, where there are two constants. I derived or I determined both the constants from the initial condition which I have assumed here. Okay. So, very easily for a given mathematical model, I can write equation of motion, solve the equation of motion, get the solution, which is dynamic response analysis of the single degree freedom system under the given condition of m present, k present, c not present and f t not present. Similarly, we look into the other remaining 4 conditions one by one in next classes, and we will see qualitatively, we will plot them and see how they look like. Okay. So, it is very interesting and very important for all of us to know that these solutions should not be memorized. Okay. Further, you will have more terms to come in, right. Do not memorize them at all. Try to keep on writing them repeatedly and get it here. Do not memorize anything and do not try to reproduce them when it is asked, right. So, do not try to memorize anything. Whenever a question is asked, understand undamped free vibration. What are the conditions present? Write the equation of motion, solve it from the first principle and try to understand the solution and then plot. And try to see what is the physical contribution of these terms there, why it look like this. So, if you relate this from the first class onwards, your dynamics class will be very interesting, and you can approach any new innovative structural system where dynamic analysis need to be done by you as a research scholar. If you simply follow this mathematically by some standard textbooks where people all these equations, all methods are explained in almost all textbooks available on earth which teach dynamics, but the way it is explained are entirely different. Okay. So, do not try to get confused. One should have mathematics background, no doubt, but still this is a very simple mathematics. If you are not able to differentiate this, I think let us assume that we are gone. But if you are able to do this and write this and extend it slightly, and remember, we should be. I am always associating to you, remember the solution from the first principles of m present, k present, c not present, therefore no c term, f of t not present, therefore there is no pi. Always related physically, then it will be easy for you to understand. Okay. Otherwise, do not get carried away by the solution and do not remember, you will never ever able to remember these terms. You will always make a mistake, you will always put x dot here and x not here. It is always obvious, or your friend will do that and therefore you will also do it. Okay. So, very easy to remember, very simple to follow. Therefore, dynamics is a very easy and easiest of all the subjects actually. It is very easy. Okay, you have to follow it sincerely from the first class onwards. Okay, and my book is also there, other books are also there, whichever language is comfortable to you. Okay, just follow it accordingly. Slowly read the papers, not the textbooks, read the research papers also, then parallel textbooks, then the class. Your knowledge level will slightly go higher and higher. If you do not do parallel reading, whatever I am doing here will look like a biggest mathematics in your ever even in life actually, they are very very elementary. Okay, then you will only leave with appreciation, no learning. By the time you start learning, I will finish the class. Okay, so that is where generally people make a mistake. Do not learn, understand and try to reiterate, do this repeatedly, therefore next class you will have 1,000,000 questions to ask. You ask the questions and we will clarify, that will be easy. Okay.